In the majestic Andes of South America, engineers have to literally cut through sheer rock walls in order to lay giant mountain roads. The work is carried out under such extreme complexity that even the slightest mistake can lead to a catastrophe. The entire project, in a single instant, can break loose and tumble into deep gorges that drop down for hundreds of meters. And yet, thanks to calculations accurate down to the millimeter, strictly controlled drilling and blasting operations, and the use of heavy equipment weighing hundreds of tons, which literally clings to steep mountain slopes, engineers managed to create winding routes. These roads follow the lines of the mountain ridges, like steel threads woven into stone, and connect regions that for centuries remained completely isolated from the outside world. Have you ever wondered how it is possible to make a road hold on an almost vertical cliff? Join VDTeam, and step by step we will figure out what happens next. In the Andes, road construction is not just a transport task. It is a direct collision between humans and one of the harshest landscapes on the planet. Many highways in Peru, Chile, and Bolivia are laid at elevations from 3,000 to 4,500 meters above sea level. Here, the thin air reduces people's work capacity by 30 to 40%, and weather conditions can change radically in just a few hours, from scorching sun to snowfall and an icy wind. In projects like these, more than 6% of the total budget goes not to the road surface at all. These funds are spent on excavation of rock, slope stabilization, and protection against landslides. That is why the construction of mountain roads in the Andes is almost always carried out according to a two-stage scheme. At the first stage, the route is laid along the outer edge of the cliff. Engineers literally cut the road into the body of the mountain, reinforce the slope with anchors and retaining structures, and also protect the carriageway from rockfalls. However, when the gradient becomes too steep or the geological structure loses stability, construction moves to the second stage. In such situations, the route is taken into the mountain, driving tunnels. This makes it possible to bypass the most dangerous zones, reduce the risk of landslides, and lessen the impact of extreme weather on the road. And now we will examine in detail each stage of building a road along a rocky massif, starting from the moment when the slope still remains completely untouched. The first step is the precise determination of the axis of the future road. The route markings and the construction boundaries are applied directly onto the rock surface in strict accordance with the design. The holes are drilled, arranged according to a pre-calculated pattern. A strictly dosed amount of explosive is placed into each one. The blasts are carried out in stages, in sections, in order to break the rock, and at the same time not disturb the overall stability of the mountain massif. After each detonation, when the stone is weakened and fragmented, excavators move onto the site. The excavators pick up and remove fragments of the broken rock, gradually clearing the construction area. The resulting material is immediately loaded into heavy dump trucks, lined up along the edge of the future road and hauled away beyond the project site. The trucks continuously shuttle along temporary access roads, delivering the debris to pre-planned disposal zones. In certain places where the terrain allows it, bulldozers push the rock straight into riverbeds or down steep slopes below, significantly speeding up the clearing of the area. After that, bulldozers come into action. They form the initial profile of the road, pushing away excess material and gradually giving the slope the required shape. The machine's blade is constantly adjusted to maintain the specified gradient and elevation marks, creating a rough but stable base for the next stages. The process of drilling, blasting, excavation, bulldozer work, and grading is repeated section by section. This is how, step by step, a continuous line of the future road appears on a dangerous and steep cliff. When the surface is leveled and stabilized, crushed stone and graded rock are delivered to the route. Dump trucks unload the material in strips along the entire line of the road. Front-end loaders distribute it evenly, preparing the base for the next layer. Then, motor graders pass along the route, forming smooth windrows and with high precision, correcting the elevations in accordance with the longitudinal and cross profile of the road. When the shape of the road begins to fully match the design requirements, water trucks enter the site. They evenly spray water over the entire surface, suppressing dust, and creating optimal moisture for subsequent compaction. After that, vibratory rollers or steel drum rollers come into operation. The machines move along the road in many overlapping passes, layer by layer, compacting the base to the specified density. On curvilinear sections or in places located especially close to the edge of the drop-off, graders continue fine-tuning the profile, forming the crossfall and ensuring proper drainage. The rollers pass along the route again, carefully compacting each layer until the road base becomes strong, stable, and completely uniform. In narrow places right by the rock, as well as where large equipment physically cannot reach, workers step in. Using handheld vibrating plates and compact tampers, they bring each section to the required density, preventing local settlement and future deformation of the pavement. Next, specialists secure safety systems on themselves and carefully climb the sheer rock wall. Directly on site, they use pneumatic drilling tools to treat uneven areas, knocking down protruding boulders and leveling the slope surface. This work is carried out point by point, with constant assessment of rock adhesion in order to prevent sudden rockfalls or slope failure. Throughout the entire process, all workers remain in a full set of personal protective equipment. Hard hats, safety harnesses, protective masks, and gloves are mandatory at every stage because the work is carried out under conditions of extreme risk. After the rock massif has been processed, the entire cliff surface is covered with protective metal mesh. It holds back small fragments of rock and significantly reduces the likelihood of stones falling onto the roadway. The next stage is asphalt paving. Before applying the main wearing course, workers spray a thin layer of liquid bitumen over the entire surface of the base. This layer ensures reliable bonding between the structural layers of the road pavement. Then the bitumen is heated with gas burners so that the solvent evaporates and the binding properties of the material are fully activated. V. During asphalt laying, the paver moves slowly forward along the route. The hot asphalt concrete mix is continuously fed into the receiving hopper of the machine directly from dump trucks. The heated screed distributes the material in an even and continuous layer, keeping it in a workable state. On both sides of the machine, there are workers who carefully monitor the edges of the mat and, if necessary, correct them with shovels and hand rakes. The heat and smoke rising from the fresh asphalt clearly make it understood. The temperature of the material remains extremely high, and the entire team must act in sync and without delays. Some of the workers follow directly behind the paver, treating joints, gaps, and curvilinear sections where the machine cannot ensure perfect precision. The paver's travel speed and the rhythm of mix supply must remain stable. Any pause can disrupt the integrity of the surface. As the machine moves forward, a smooth black strip of fresh asphalt gradually stretches behind it, visually completing one of the most difficult stages of building a mountain road. After the asphalt laying is completed, the surface is treated with high-pressure water jets. This makes it possible to remove remaining stones, dust, and excess material without disturbing the structure of the surface. The nozzles are moved evenly to ensure the cleanliness of the road and preserve the quality of traction. Gradually, the asphalt cools and turns into a strong, monolithic layer, clearly emphasizing the bends of the route along the slope. If you look at the finished route from above, it resembles a black ribbon thrown over the sheer wall of the mountain. This is a visual completion of a large-scale engineering job performed under conditions that are rightly considered among the harshest on the planet. However, there are sections where the rocky massif is practically vertical, and there is physically no space left for further rock excavation or for widening the roadway. In such places, the road has to be literally suspended along the mountain slope. For this, a system of reinforced concrete support columns and prefabricated modular elements is used. Instead of cutting deeper into the mountain, engineers move to a vertical method of construction, using the space under the road as a load-bearing zone. First, massive concrete columns are erected directly into the bedrock. They serve as the main load-bearing frame on which the entire road structure later rests. Because of the extreme terrain, most materials cannot be delivered by standard transport. Therefore, structural elements are installed using cranes, specialized equipment, or carefully lowered from above into the exact design position. After the columns gain their design strength, the installation of the road deck begins. Sections are laid one after another like giant construction set elements directly on the mountain slope. Each module is manufactured in advance to standard dimensions and includes steel beams, concrete slabs, and connection nodes. This approach significantly reduces the time of work directly at the site. All workers involved in the installation are constantly secured on safety lines. The work is carried out in close coordination with the crane operators because the positioning accuracy of each element has critical importance. As the modules are fixed onto the columns, a continuous line of road gradually forms, repeating the natural outlines of the mountain slope. After the deck installation is completed, the road surface is laid. Protective barriers, drainage systems, and safety elements are installed, ensuring the durability and reliability of the structure. This method makes it possible to build roads where it was previously considered impossible, and at the same time it substantially reduces the volume of blasting and mountain works. It represents a combination of modern engineering thought and adaptation to the natural landscape, allowing infrastructure to exist even in the harshest mountain conditions. But there are situations when it is impossible either to cut the road into the rock or to suspend it on columns. In such cases, the route is directed straight through the mountain massif, creating a tunnel system. From this moment, the project seems to take its first breath. At depths of hundreds of meters underground, pressure, dust, and heat can make the air deadly dangerous in just a few minutes. Engineers need to create an artificial life support system that will allow people to work underground for hours. From the construction center upward to the surface, vertical shafts are drilled with a diameter from 4 to 6 meters and a height up to 200 meters. Through them, fresh air is supplied and exhaust gases are removed. Inside the tunnel, sensors continuously track oxygen level, temperature, and the concentration of toxic gases. Powerful jet fans automatically regulate airflow, maintaining safe conditions. Ventilation shafts are created by the raise boring method, in which the drilling head is controlled from inside the tunnel and moves strictly upward with almost perfect precision. After the work is completed, this system becomes the true lungs of the project, allowing hundreds of workers to labor under the mountain while continuing to breathe vital air. Outside, the construction site is wrapped in a cloud of dust, and deep inside the mountain, the assembly of a colossal machine begins, a tunnel boring complex. This aggregate is rightfully considered a symbol of the modern era of infrastructure. The process of installing this machine before the first launch is a most complex engineering operation, requiring absolute precision and flawless coordination of hundreds of specialists. All elements of the tunnel boring complex are delivered to the site by hundreds of specialized transport units. Each module, from the support frame and the operator's cabin to the hydraulic systems and the cutting head, has a mass from several tens to hundreds of tons. The heaviest component, the cutting head, weighs more than 100 tons and reaches almost 15 meters in diameter. To place such large elements, auxiliary tunnels are expanded in advance and temporarily reinforced with steel structures and sprayed concrete. In the limited space, illuminated by hundreds of industrial lights, the modules are connected and aligned using laser sensors. The allowable tolerance is no more than 5 millimeters. Powerful hydraulic jacks gradually lift the cutting head, connecting it to the body and the tail section of the machine in a strictly defined sequence. After the assembly is completed, the tunnel boring complex stretches to almost 100 meters. This is the equivalent of a 30-story building laid horizontally. Thousands of mechanical components are perfectly fitted to each other, forming a single steel organism ready to cut through the hard heart of the mountain. In the central operator cabin, electrical, hydraulic, and pneumatic systems are activated simultaneously. At this moment, the mountain seems to shudder slightly. the tunnel boring machine begins to move. With a length of about 100 meters and a mass of more than 3,000 tons, the aggregate advances slowly but with colossal force. Thousands of parts work in perfect synchronization. At this stage, the cutting head is already deep into the rock, while the rear part of the machine still continues assembly in the startaway chamber. The process requires flawless coordination between the systems of power supply, water supply, air supply, and rock transport. Any failure here is unacceptable. In the front part of the machine, 4 massive hydraulic cylinders press the cutting head against the rock with a force of up to 500 tons. 23 alloyed disc cutters rotate with enormous torque, crushing rock layers whose strength is comparable to steel. One working cycle advances the machine by approximately 1.2 meters and takes about 30 minutes. In one shift, more than 50 such cycles are performed. The crushed rock is collected and automatically transported outside by a conveyor system. At the same time, high-pressure water jets continuously cool and clean the cutting head, reducing friction and wear. After the completion of the cycle, the gripper shield moves forward, the hydraulic supports are fixed into the tunnel walls, and the process begins again. This rhythm, pressing, razrushenia, advancing, repeats again and again, day and night without stops, until the tunnel is fully completed. This is how underground arteries are created, changing the map of entire regions. In projects of colossal scale, such as the European Santa Lucia Tunnel with a diameter of almost 16 meters, or the 57-kilometer Gotthard Base Tunnel in Switzerland, tunnel boring machines work around the clock with astonishing precision. However, today, the leader of this underground frontier has become China. More than 1,000 tunnel boring complexes simultaneously lay railways, metro lines, and hydropower tunnels, demonstrating the country's streamlania to conquer depths with the help of technology. When the boring is completed, the work does not end there. Engineers, having replaced drilling equipment with measurement instruments, return to the tunnel. Now every meter of the concrete lining must prove its reliability. Pressure sensors and ground-penetrating radars scan the walls, detecting cracks thinner than a human hair. High-frequency ultrasonic systems and 8K resolution cameras check every bolt and every seal. In the control room, hundreds of indicators in real time monitor the operation of ventilation, smoke detectors, drainage pumps, and a reserve-new power system with a capacity of 10 megawatts. All systems undergo testing in strict accordance with international safety standards. Every value, every vibration, and every parameter is recorded and analyzed. And only when absolute precision is achieved, the tunnel is officially recognized as ready for operation. It becomes a symbol of engineering perfection and human resilience beneath the thickness of the earth. You have just gone with us through the entire path of creating mountain roads, from routes pressed against sheer cliffs and suspended structures on concrete columns, to sections where the road passes through the very heart of the mountain. All the information used in this video was collected and carefully selected from various sources. If you still have questions, be sure to write them in the comments. And with that, we say goodbye to you. See you in the next videos.